For us, the story of isolates starts with this chart. This is a performance chart. And by looking at the performance of the three different systems here, we're going to develop an understanding of why isolates are interesting, why you should pay attention, why this might be a different way of doing compute that will become more popular in the future. The blue line on the top is Amazon Lambda. It represents the best in class for traditional container-based serverless compute. And each of those containers run processes, just like any other piece of code that you've ran for the last 50 years, a process running on a machine somewhere. The green line is Amazon's Lambda at Edge product. It's the same technology, but deployed to many locations around the world. And we should generally expect that to be faster for the same reason CDNs are faster. By running it all around the world, it gets closer to our testing locations, which are also all around the world, replicating the experience that a global user base might have. So we should expect Lambda at Edge to be faster. And then the red line is Cloudflare's isolate-based serverless product, also deployed all around the world, but using a different technology called isolates. And the performance we see here is probably going to be somewhat similar to the performance of any other isolate-based system that was deployed that way. Cloudflare system is just the most robust, and so it's the easiest one to test right now. The chart itself shows response time in milliseconds on the left, and then it shows percentile on the bottom. So what that means is if we look at the 50th percentile, for example, we are seeing that 50% of the tests against our worker, our Cloudflare isolate-based serverless code, completed in 82 milliseconds. And all three of these examples are running the same code. They're all running an algorithm called PBKDF2, a password hashing algorithm, with the same setup and the same settings, roughly the same code. So here we see that half of the requests completed in 82 milliseconds. When we look at the Lambda at Edge, it took 358 milliseconds. So those users would have experienced significantly longer wait time to get that response back, and it would have taken ultimately about 4 times as long. And that continues being true when we look at the 90th percentile, for example, where it's 591 versus 221 milliseconds. Finally, when we move all the way down to a single Lambda running in a single location, which is the way most people deploy serverless functions, we get dramatically worse performance. And this is primarily because it just takes a long time for the speed of light to travel all the way around the world. When you deploy to just one location, things get slower. So in this case, it's taking 864 milliseconds to do what took our worker 82. So it's more than 10 times slower. And those users are going to be sitting around waiting for about 700 milliseconds before they get a response. All three of these have 128 megabytes of memory allocated, and again, they're all running the same code. So we understand why the Lambda at Edge would be faster than the Lambda. Lambda at Edge is deployed all around the world. It's closer to our testing locations. But the real interesting question here is how this red line can be so much lower. Most people would tell you that deploying a containerized process, maybe a serverless one, in many locations all around the world is about as fast as a computing system can possibly get. How is it possible to build something that ultimately delivers an experience that's so much faster? And the answer to that is going to end up forming the bulk of this video. But there's one other way that we can think about these three systems while we're looking at this chart, and that is in terms of cost. Because these three lines do not represent the same cost to you as a developer. And conventionally, you probably would think the faster thing is more expensive. But that doesn't actually prove to be the case. And that's another thing that we're going to explain by talking about how isolates are a little different than other forms of compute. The blue line here, a conventional Lambda, costs about $1.83 per million requests. And that's because we're doing about 800 milliseconds of compute and we're using 128 megabyte Lambda, which is the same size as the worker and as the Lambda at Edge. And that Lambda costs us about $1.83 per million requests. Now, that's just a starting price. Amazon also charges for all sorts of other things, including the requests. Going through some sort of API gateway can be very, very expensive. The bandwidth they charge for, the DNS requests involved they charge for. Ultimately, that it can cost easily $5 per million requests. The Lambda at Edge is generally 3 times more expensive than Lambda. That's how Amazon prices it. So if this is $1.83, the Lambda at Edge is going to cost $5+, not including all those other fees that you have to add up. Now, the green line, which again we talked about being about 4 times slower than the worker, is $5 per million. The worker, though, is 50 cents per million, flat, no additional fees of really any kind. And that comes from Cloudflare's workers product, but this would be true in a lot of ways with any other form of isolate-based compute. Somehow we are able to do the same operation significantly faster, delivering a better response to users. And if we look at the 90th percentile, you can see just how drastic that is. Again, about 3 times faster, saving the user half a second. And we're able to do it for a tenth the price. And that is not because Amazon is bad at pricing or Cloudflare is losing money or anything like that. It's because isolates allow for globally deployed edge computing like this in a way that's fundamentally cheaper. And that is why, one of the reasons, isolates are probably going to make a bigger and bigger part of the way that we build computer systems in the future. And let's take a step back, though, and let's talk about where computers started and what an isolate really is. This is the Lions Electronic Office 3, a computer built by a tea company. Why did a tea company build a computer? Because no one else would. They needed a machine that could allow them to do all of their accounting and tabulation, the things that a business relies on in order to function. But at the time, in the 1950s, this type of device just didn't exist at any price. So they decided to build one, and then two, and then finally three, the Leo 3, the Lions Electronic Office 3, the circuit board that we see on the right. Now, this tea company wasn't just good at making tea, they were also pretty good at making computers, and they invented something that no one else had really ever done with a computer before, multitasking. They figured out it was possible to run not just one program at a time on a computer, which is kind of what you would do with an old school mechanical census tabulator, but to run multiple programs all at the same time, to allow the machine to run little bits of each piece of code in turn, such that at the end of the day you actually had executed maybe an accounting program and also a warehousing program and also an inventory program. It seemed like all were running at the same time, but actually the processor was able to switch from one piece of code to another very, very quickly. This is sort of what that multitasking would look like. The processor would spend a certain amount of time running one piece of code and then very quickly move to another piece of code that it would run. When you zoom far enough out, it looks like they're all running at the same time, but it's actually rotating between them. This is the same model of multitasking that every computer has used since, including the computer or phone, tablet that you might be watching this on right now. After the Leo 3, the tea companies of the world got out of computing and universities moved in. This is the GE645. The 645 was a warehouse-sized computer that was built specifically for MIT to invent a new operating system, an operating system called Multics. Multics was the first operating system to introduce all sorts of other concepts. They copied the multitasking or reinvented multitasking and also came up with all sorts of security concepts and even the hierarchical file system, the idea of files and folders divided with slashes. Multics was a huge revolution in computing. Unfortunately, it was very expensive to run and very complicated. And like so many other things in the history of computing and technology, the complicated thing did not win. Instead, some of the Multics engineers went on with a much smaller and easier to find computer called the PDP-11 to build a new operating system called Unix, not Multics, Unix. And Unix became the grandfather of so much of computing today. Unix has some descendants including Linux that you may have heard of, and now a lot of the concepts that were born in Unix live inside every operating system that we use in virtually every device all around us. Unix shared that same multitasking concept, that same ability to run multiple programs at the same time on a single computer, by really rapidly switching the processor from running one piece of code to another. As I mentioned, that concept lived on in Linux. Penguin is the Linux moniker. And Linux brought all of this technology into a form where it could be used on any computer for free. And that made it really, really popular. It's particularly popular in servers. Virtually every server on Earth runs some version of Linux. And so inside of it, it is doing that multitasking in the very same way that the Lions Electronic Office was. It's taking all of the programs that have to run and allowing each to run in turn, giving each program complete access to the processor. And this has been a really, really powerful and flexible system that has brought in the modern computing age. And it has been used at very great scale. Inside data centers, you often find thousands of Linux servers, and it's possible now with companies like AWS to rent these servers not just by the month, but by the hour. So I can hop onto the AWS dashboard and fire up 100 or 1,000 Linux servers and have them running for me instantly, able to execute all sorts of computing tasks. And so we're still using the same model of multitasking that we've seen for so many years, but now it's available in a very flexible and easy to use format. And that flexibility is increasing. There's a product called AWS Lambda, a serverless compute product, that takes all of that and packages it up into a form that's really, really easy for developers to use. A developer writes a piece of code, and they don't have to think at all about where it's running or how many servers might be running it. They are getting these processes, the same unit that was allocated by the Lions Electronic Office, allocated to them automatically, scaled up and down as necessary to handle however much load they might get. So the concept of the process is very, very successful and very smart and very clever, very useful in a wide variety of circumstances. Unfortunately, it's also started to fall apart. One place it falls apart is in the world of edge computing. For many years, we've thought about computers as living in a specific place, in a specific building or a specific region. When you go onto a cloud service like Amazon's and decide that you want to provision some servers, you have to pick which region they live in. They might be in US East 1, which is somewhere in Virginia, or they might be in US West 2, which is somewhere in Oregon. But you have to pick a specific location where you want your servers to exist. And that's no different than back in the days when you would have to buy your own racks and buy your own hardware and install it into the basement of your office. Unfortunately, the world has become a very global place, and so it's very common now for businesses to have customers literally everywhere, every place around the world. And that doesn't map well to a world where your servers only exist in one location. Unfortunately, it just takes the speed of light too long to get all the way around the world to provide a really fast experience everywhere. So there are companies like Cloudflare, this is a map of Cloudflare's network, that have started placing servers in more and more and more locations around the world, trying to build a network that's so dense that you can have servers that live really close to every person on Earth. Each location might be getting less traffic, but the fixed cost of keeping all of those processes running in all of those locations ends up making it prohibitively expensive. For a really good look at that, it's valuable to look at how much memory Node.js, a really popular way of running code, consumes. If you start a basic Amazon Lambda running Node.js with no real code in it, it will consume about 35 megabytes. If you deploy that to 200 data centers that each run about 32 machines each serving a website, which is common for a CDN, you end up with 200 gigabytes of RAM being consumed to run essentially nothing. And as your program uses more memory and does more, that adds up really, really quickly. It becomes very cost ineffective to try to keep all of those machines running all of the time in all of those locations around the world just to run your piece of code. It makes it virtually impossible for anyone but the largest enterprises to think that they could use this edge computing technology. Unfortunately, edge computing is really important. Performance on the web has not gotten better all that much in very recent memory, and the only way to improve it is to be able to run code in more locations. Additionally, legal regulations have started to make it really important to be able to run code and store data in the countries and cities where users actually live. It's not okay anymore to ship a user's data halfway around the world just because it's more convenient for the developer. We need to be able to run code everywhere in a way that's as ubiquitous as the internet. Another reason that the traditional processing model has kind of fallen apart has been that way that multitasking happens. As the processor core has to switch from running one piece of code to another, it does something called a context switch. A context switch generally is considered really cheap. It doesn't consume that much computational time. Unfortunately, as you have a server that's supposed to run more and more pieces of code, and in this world of serverless computing, a lot of these pieces of code are very small and can run across many machines, and so you could conceivably have a machine that's responsible for running potentially thousands of different pieces of code. The context switches start adding up. They become incredibly expensive when you're trying to run 1,000 pieces of code at once, all of which are receiving different requests to load different websites. And it's just not acceptable to try to run less of them because then your machines become prohibitively expensive again. We also run into some fundamental issues with the APIs that exist and were developed all the way back in the Unix days. In order to run many different pieces of code, an operating system would give each piece complete access to the processor and tell it that it's able to do whatever it needs with this processor. Unfortunately, that's really risky, and the operating system has to do a lot of work to try to ensure secure isolation between all of the different processes to make sure one cannot steal data from another. These systems that were developed to try to create those guardrails end up being really time consuming. And in some pieces of code, they make the code run as much as a third slower than it ordinarily should because the operating system has to do so many security checks before it's able to execute code. That starts to add up and eat up computation that we otherwise could use to do productive purposes. Additionally, we run into a problem called cold starts. A traditional process, a traditional runtime like Node.js, was meant to be deployed maybe once a week. And in that world, it's totally okay if it takes half a second or 10 seconds for it to start up and start receiving and serving requests. Unfortunately, the serverless world works a little differently. We want our node to be able to spin up in response to a request over the internet. So a user loads your website, and if more capacity is required to serve that request, your virtual machine, your Node.js instance, your process is turned on or scaled up in response to that request, and then it immediately serves the response. That is a magical system for a developer because it means they don't have to think about deploying infrastructure or scaling it up. It all happens magically and automatically. Unfortunately, those cold starts take a long time, and it doesn't make a lot of sense to move into an edge computing future where performance is going to be so much better for everyone around the world if at the same time you also are slowing everyone down with these cold starts that happen anytime the popularity of a website spins up or a new version of a website is deployed. The cold starts result in slower requests, and that's just unacceptable in the modern world. So what we have is a much more modern, much more flexible way of deploying code that's built on top of an infrastructure that is now 50 years old. Now, that infrastructure has taken us very far, and there are a lot of tools that work with it really well, a lot of ways of deploying code that we all like. But it might make sense to look at other models of computation, other ways that people have invented of running untrusted pieces of code to try to answer the question of maybe one of those can solve the computing future, the edge computing, the serverless needs that we have a little bit better. So let's start over. We need to run code on distributed machines in an isolated way, and we need it to only use the memory and the CPU that we have available. We also don't want to think about regions anymore. We want all of our code to run everywhere. How can we do that? Well, there is one answer. There's one tool that it turns out does this pretty well already. It's something that Cloudflare figured out a few years ago, and it's called the web browser. The web browser that you very well may be watching this video on right now solves all of these problems somewhat incidentally. It has to spin up code really, really quickly because when you load a new tab, you need that tab to load fast. It has to run code in an isolated way because you can't have one website able to snoop on another and maybe steal your banking credentials. And it has to use really minimal amounts of memory because we all care that our web browser does not suck up all of the memory on our computer, and people load so many tabs. So much work has been put into trying to reduce the memory overhead. So you have JavaScript WebAssembly engines built into web browsers that do this miraculous thing of solving all of these problems for their own purposes. And the next question is if you can take that technology, in Google Chrome, the engine is called V8, and move it into a server and use this V8 engine to do all of your server-based computing inside a single process. And that's what this looks like. Instead of having a process for every piece of code that you might run, you have one big process. So the operating system sees it as a single process, no more multitasking. Inside of that process, you run one virtual machine that's responsible for running JavaScript, running WebAssembly, and that WebAssembly can be compiled from all sorts of different languages that a user might write. And each piece of code gets a unit called an isolate. And an isolate is so much smaller than a process because it doesn't get direct access to the processor to run whatever it wants. It has to be run by that virtual machine. And that means all it really needs is the code and the variables that it needs to use in order to do its computation. It doesn't need its own copy of the virtual machine like you need if you're going to run a node Lambda. And it doesn't need to go through all the same in-depth security checks because it's never going to get the keys to the castle. It's never going to be able to directly run code on the processor. We have moved everything up a level. And by moving it up a level into a single process that we have control of, we get to answer all of these questions in a more modern way than traditional operating systems did 50 years ago. So what do you get? Well, these are stats that come from Cloudflare's platform workers. And on Cloudflare's platform, you get 3 times more compute per dollar than a traditional serverless platform. And that's pretty amazing because these aren't running in a single location anymore. They're actually running in many, many cities around the world. So edge computing, which is generally considered to be more expensive, is actually significantly cheaper because of this better computational model with lower overhead and lower resources. And those resources are really easy to see. It's about 10 times less memory. So a empty isolate that's ready to run some code is about 3 megabytes of memory as opposed to 35. And the cold start time is shockingly lower. It's 100 times lower. The average cold start time of a Cloudflare isolate is about 4.4 milliseconds, as opposed to approaching 500 for a node Lambda inside AWS. And that is an amazing difference. Because when you can start code that quickly, you really can start it in response to a web request coming over the internet. Most web requests take at least 10 milliseconds just to travel from wherever they originate to the server that's going to respond to them. So if you can start your code in 4.4, you're adding a negligible amount of overhead. It is truly possible to scale from 0 to 1 million requests per second while expecting none of them to get a slow response and never having extra resources provisioned. It's also amazing when you start thinking about how this works around the world. If it's this cheap to spin up new code, it suddenly becomes possible to serve a request really close to where it originated really cheaply. If a request shows up in Mongolia or in Madagascar, you can spin up a copy of the code that's going to respond to it, the isolate that's responsible for that website, and respond to it almost immediately without paying for the bandwidth of sending that request all the way around the world. And that means it actually becomes cheaper to respond to requests locally, to offer better performance, edge computing all around the world in a serverless model, the dream of every developer, than it was to try to send it all the way around the world to somewhere like Virginia or Oregon. So let's return to our performance test. Ultimately, what we're seeing here is not magic, and there are a lot of caveats. You can't use isolate-based compute with things that were originally built to run as a process, for example. They expect complete access to a processor and to an operating system, to a file system. They expect these things that we just don't provide in an isolate-based world. What you can do, though, is run many, many, many instances of these on a single machine at a single time, which makes them cost-effective to deploy and distribute all around the world, to run your code everywhere. And it also makes it possible to start these up so much faster and with so much less overhead than a traditional process, container, Kubernetes pod, or even serverless function. So what applications is that perfect for? A lot. Most web services, for example, would really benefit from being deployed all around the world and from being able to scale instantly everywhere. And they really never needed the system call interface that traditional operating systems invented. So the final question that we have is, given this world, what is the future going to look like? Is edge computing going to be an esoteric thing that's used for virtual reality, as in this picture? Or is it going to be the way that all systems are built? Are isolates going to replace processes in a lot of the ways that we design software systems? I personally believe yes. I believe that most applications developed far enough in the future for this to apply will be written in the way that the internet works. The developer will write the code that represents how they want things to work, and they will not have to care where it's executed. It will actually get executed on maybe thousands of machines around the world, wherever their users are. And if they suddenly become incredibly popular, it'll be executed more, and they won't have to do anything in order to make that happen. We have really good models of this already happening today, like the web browser. When a front-end developer writes code, they don't know what machine it's going to run on, but they are able to successfully write code that works across a wide variety of them, thanks to web standards. The exact same thing is going to happen for back-end programming. Backend developers are going to write the code that represents what they want to happen, and it's not going to be their problem to worry about where or how it gets executed. It's going to be executed ubiquitously by thousands of machines all throughout the internet in a way that's much more reliable and performant than any model that a tea company could come up with, or a bookstore.